My name is Kayvan Alikhani. I'm the Senior Director of Technology at RSA EMC. Started a company called Passband in San Francisco, just a block away from here, and we recently joined RSA like as of 90 days ago. So the presentation's been overlaid into the RSA EMC format, but originally came from a starving startup a couple blocks away. And the idea behind Passband and the work that we were doing all around making it easier for people to identify themselves when accessing applications and content on mobile devices. And here today I wanted to talk about what we found and the where, when, how, what, and why in terms of securely storing and accessing information that you find sensitive as it relates to, thank you so much, as it relates to Android devices. What's actually being stored, as you all know, from one side, there's some certificates, whether these are certs that are issued by the certificate authority or they're certs that have been provided on personal certificates. And from the other side, we talk about obviously sensitive data, be it data that you're storing because it's important to your application, user credentials, passwords, the usual suspects, things that are sensitive and important to the user and to the provider of the content. So ultimately we see three types of storage in terms of where is this content being stored. From one side we have applications that primarily use the device itself as a means of storing this content. So you basically take a Android key store, which is a built-in mechanism of storing and keeping track of information, particularly certificates on the device. You also can do the same on, for example, on an SD card. Using secure elements becoming more and more popular in terms of finding ways of storing the cryptography, the method of key generation, and actually the security associated with the content you're storing and putting it on a tamper-proof and what's called a non-debuggable piece of hardware that either resides on the device or elsewhere. Sometimes we see sensitive data just cached in memory, maintained, and generated or retrieved from a server on runtime. And we see a lot of trends in terms of password vaults, or applications that use a mechanism of storing structured encrypted content in a SQLite or similar database, and ultimately persisting the data on the client side, on the device side. In a hybrid model, we see that the information is not necessarily stored all on the client, so you have basically maybe a split key scenario where some of the information is on the device and the rest of it is stored on the server, where some information is being backed up by the server, synchronized with the client for access, and then other scenarios where the information, sensitive info is purely stored on the server. The device, if rooted, if hacked, there's nothing there. It's all retrieved runtime, used runtime, and upon application shutdown, other than there was in the memory, nothing can be retrieved from a sensitive or, let's say, credential information. So those are the types of storage that we've seen in terms of the sensitive content. Now we're going to go through some of these scenarios and talk about the pros and cons of each. Trust source, which have been around in 4.x, specifically I would say 4.3 got a great facelift, and in terms of the key store, a public API to store and use multi-user now, as of the latest editions on Android, app-specific key data. So you have 3 or 4 users using the same Android device, but you want to store key information or credentials or certificates associated with each one of those users. You can use the public API that's provided as part of the key store. And you can also see where the information is stored, whether the information is stored on a hardware-based secure element, as it's done specifically with Nexus 4 and 7, or software-based, where in the Galaxy Nexus there's basically software-based storage of the information that's stored in the trust store. So you can actually use the Android key store provider, JCE provider, and then use the Android key store as a type parameter, and then arrive at where the information is actually being stored. And that's important to some people, and it's a great way, as I said, it's been greatly improved and stabilized, and the features have been enhanced in 4.3. The overall challenges when information is stored in files, aside from the trust store, which we'll talk about some of the issues with it later, but the challenges when you're seeing, for example, security information in terms of user credentials for an application, let's say, I don't want to pick on Dropbox, but Dropbox is a file and the credentials for the user are encrypted and dropped into that file, or Facebook was doing the same for Android and iOS. And the challenges we've seen with them are that the device gets rooted, you USB into the device, the protection that was maybe use a key to unlock the device is completely bypassed because now you're coming through a different path and getting access to the file system. And now you can start brute force attacking the file and finding the password simply by looking at the encryption that's being used. The actual key, the actual encrypted content is now visible to a hacker. In some cases, it wasn't even encrypted, it was clear text. And so now you get access to what was supposed to be a clear-cut credential that was supposed to be stored on the device. So file-based storage has its challenges, specifically when the credentials are fully resolved within that file. It poses a big threat, specifically in an Android operating system. And as I said, a lot of times we've seen systems that are relying on the Android front-end locking mechanism to prevent access to the file system, but USB access and rooted access really bypass that whole paradigm. The other challenges that we've seen is that in terms of file-based storages, where they're using, for example, a file and encrypting content and storing all that content on the file. So the app creates a file and then makes a mistake and sets the UMask for its process. So it doesn't set their UMask, I'm sorry. So as a result of that, the file becomes world readable, world writable. And what that means is any rogue application can now control the device, reconfigure it, impersonate, and use that app to actually execute arbitrary code. So essentially using UMask for the process, setting it is essential, otherwise it becomes readily available to any application. It becomes very easy to hack that. We've seen this as a vulnerability not just on applications, but on security applications. The security application has been written, UMask has now been called. The app that was supposed to be acting as a security credential manager is easily compromised and used to actually control the device. So that's another challenge that is a risk assessment. Database storage, where you're seeing password vault type applications. Take, for example, a application which takes all your passwords, password managers. So instead of entering passwords in websites, they store this password in a collection inside the database and then make it client-side native available on the Android device. And the challenges that we've seen through an analysis we did, and also a group of very well-done reports that compared probably 20 or 30 of these password vault type applications, was bizarre, to say the least. The information would be encrypted inside the database with a master password that was in clear text, stored into the file. So you had access to the file, you got the master password, you could just guess at the cryptography, and now you were getting access to information. Weak cryptography, weak algorithm, password was cached, master password in clear text. All you have to do is look at the cache, walk through the cache, and root it, and you get access to it. So even though it was not persisted in clear text, but it was cached in clear text, and that's another issue that we've seen. The other issue, just in general, is that they're susceptible to brute force attacks. So if the device can be rooted, which it can be rooted, and the password that the users are using are pins, popular is 123455555, in our household 0000, so my 5-year-old can log into the iPad. So you talk about these kinds of passwords so easy and so quick. Once you have that file copied over, use a very mid-range average server, and within literally hours, a couple of hours, you can decrypt that password and get access to the sensitive content. So the challenge is there. Now, from the other side, you may say, well, why don't you enforce users to have to put in 16-digit passwords or complex uppercase underscore question marks when they're entering passwords? And nobody wants to do that. End users are just not happy with that kind of inconvenience in the mobile world, and that's why you typically use very simple pins. And a lot of the applications that are actually living inside your mobile device, not because they don't know how to do security, but because they don't want to inconvenience the user, they don't challenge the user with additional pins or passwords. So if you're using Android's device past that pattern or pin or face biometric, whatever method that you're using, now this device If you're using Gmail, if you're using Calendar, if you're using Contacts or typical other apps, Dropbox, Drive, they're not going to challenge you with a password. They're going to make it actually very difficult for you to enter the password, caching it, remember me. Why? Not because they don't like security, but because they just don't want to inconvenience the user to have to enter a complex password and maintain it. So that issue of convenience has led to lowering the bar in terms of security. So one of the items that I mentioned in terms of the where, as opposed to the actual local device, would be secure elements. So we looked at various forms of this. We actually built a solution specifically around secure elements, which I can describe to you what we did. And in the case of secure elements, the idea is you're running everything inside an app. The application is running on Android. Android is an operating system. At the once getting access to a device at the root level, you can do whatever you want to do with the device. So secure elements really solves this in a nice way. It says that you can take that information, that credential, that sensitive piece of information, and put it onto a SIM card or use a built-in smart card. And ultimately, also maintain the information in terms of the cryptography, the method of key generation, and actually the keys themselves on that tamper-proof device. And what that brings to the table is now the actual value of the keys, the information that was the secure data, is not visible to anybody. And there's no API, there's no method, there's no debugging method of you seeing or getting access to that key. And that makes brute force attacks practically impossible, because the API or interface that a secure element provides is get or set, and it can see that it's getting requests for comparison over a period of time. It can lock itself, it can stop responding to requests for unlock. And so as a result, it can significantly increase the amount of time. I mean, days, months, and years before somebody could brute force attack just to retrieve one, use a brute force attack just to unencrypt one password from a secure element. And so that brings a lot of nice value. The challenges, which we'll talk about later, is in terms of impersonating the secure element and taking control of the device and impersonating the secure element. So now, ultimately, in order to talk to the secure element, you need what? You need an application, right? And so if I can come into Android, remove that application, put another APK, and impersonate the responses from that application, now you're going to start typing in your password, and I'll be capturing that. So the challenge is really a little bit further than that. It's not just a secure element, it's the ability to impersonate some applications, and we'll talk about that. Other approaches that we've seen successfully implemented, and that's one of the ones that also that's the approach we took, was wearables, or devices, like devices that we use NFC or Bluetooth to communicate with the device pair and unlock the application. So what we did was we basically put the cryptography, the key generation and maintenance on the device. You would tap on the wearable, move your wrist, and that would unlock your application, it would launch it. And the idea was that the user now doesn't have to necessarily enter a very complex password. You can hack away on that device all you want, as long as you don't have this wearable, which is tactical, you're not going to get access to the key information. And that, as a result of being in a separate device, you have a higher chance of protecting that information in terms of the device gets lost, but this one is still with you. Obviously, it could also be a pain carrying now another device with you everywhere you go, just to get that level of security. But those are the type of devices that we're seeing: Bluetooth, low energy Bluetooth, NFC, USB connected, and also network-based devices that peer the device over the network, not necessarily over a near-field communication protocol. And then ultimately, applications that split the key, so that part of the information is on the device, but the other part is actually stored on the server. And in this case, the accessing the device will yield only part of the key material. The other part of the key material for your secure data is actually stored on the server. And for secure elements, Android actually, there's an initiative, SDK, SIM Toolkit, and there's also a implementation of it called Seek. Seek is Android reference implementation of the SIM Alliance for Open Mobile API specification. And so this provides an ability for vendors, hardware manufacturers, Android manipulators, if you will, people who make their own version of Android operating system, to build their own, basically, SDK. And so now they can say, talk to me, I will talk to the secure element, I will store your credentials on that, and I will maintain the information relevant to that. And Samsung's built their own. Also, there's an open source version of that, which is Seek for Android, and it's been done very nicely in terms of using the Android radio interface layer to communicate with the secure element, or be it local or remote. So Seek provides a very nice entry into that. The challenge with Seek is it's not necessarily on every device. And the other challenge with it is, as we'll see a little bit later, for secure elements is that smart APIs can be compromised on a rooted device. Again, so even though you put a secure element on the device itself, if you can root the device, you will replace the APK that represents this secure element application, and now you start simulating, impersonating the responses as if you are the secure element application. So that's one of the threats that we saw with SEs. The other challenge with SEs is that not all devices have SIM cards. I don't know if you bought these Android tablets that are Wi-Fi only. They're not necessarily providing a wireless SIM card that's programmable. Not all SIMs are programmable, period. Some vendors just block access and don't allow for programming of the SIM. Depends on the operating system support. Not all versions of Android up until 4.3 provide the full level of programming necessary for SEs on a SIM card. And as I said, root access really bypasses it. The other challenge with the SIM card or SE approach, secure element approach, is you have to load that cryptography, that secure application onto the SIM card. And in order to do that, you can't do it over the air. You have to use the global platform load and actually load an application onto the SIM card to achieve secure element functionality. The other challenge, so I suggest that you use a wearable or another device, or for example, pairing your laptop with your Android device, or pairing your Android with your tablet. And the challenge with that is that ultimately users forget to carry it. The same problem you've seen with tokens. You don't have it with you, and now you can't log in. And also it requires enrollment, so it's not functional out of the box. The other challenge with communicating two devices is battery life, right? The moment you turn on NFC or Bluetooth, or be it even low energy, you ultimately are draining the battery, and also the user has to remember to turn it on, and if they turn it off manually, now the application has to inform the user to turn it on. It's a bit of an inconvenience. And obviously the network-based approaches that we've seen and have implemented requires network connectivity, which is not always available. We've seen also this unintentional pairing, where the actual pairing now becomes a rogue application, knows that in order to provide security, you're actually using Bluetooth or NFC, and it impersonates that protocol. And so now, just by being in the vicinity of your device, it can pair and it can impersonate and start basically making it look like you're entering the information into your paired device, where in fact information is being sent to a rogue application. We've seen implementations of secure element based on Seek. In fact, Google Oath authentication, which is basically two-factor authentication, something you have and something you know. And this something you know would be a second device that's generating a soft token, 7-digit token periodically. And the key generation, management, encryption, all of that gets loaded onto the SIM card by using JLoad, and basically load the application that has been written based on Seek onto the Secure Elements global platform. And then you couple that with another device or Google app for two-factor authentication. We've also seen password vaults, which actually use the secure element or the SIM card to store the encrypted keys on the device. These are the more secure and higher level of reliability password vaults. And really, you want to look for ones that are essentially encrypting and key management. All of that is on the secure element, not just the keys themselves. You really want the entire process to be on the SE. And they really use the application logic only to access the secure content, not to perform cryptography or manage the keys. The other approach that we've seen is basically the split key approach. So basically, one part of the information is on the device and the other part is on the server. And one of the interesting challenges is sometimes it's not some of this on the server. They actually end up backing up or retrieving too much information onto the server. And one of the most recent interesting ones that I saw was use Android. You're probably giving Google all your Wi-Fi passwords. Very bizarre. So basically, the actual passwords that you enter into your Wi-Fi connection in Android, Google by default is backing these up. And they're backing it up in clear text. So if that information is being hacked either in transmission or in rest at Google, you have access to all the passwords that are needed to access this person's Wi-Fi information. So that's why, what I mean by only part of the information. Maybe the information that should have been stored should have been the encrypted data, and the user's password would have been unencrypted. So the user's password should have been the content that would have been necessary to unencrypt and access that data, not store the information in clear text, pass it, save it on the server. Now, the challenge with that is what I just mentioned. So encrypt the data, but the encryption requires the user input, to unencrypt the information. So how do you provide that? That makes it very interesting, because now the information that's being, the information that's being stored on the server only has the encrypted data. It doesn't know how to unencrypt it because it requires user input.
The company as big as Google, in that case, are they legally required to be able to unencrypt the data at some point?
I mean, that was really the question. If you read this article, it was really well written. It was sort of like, why does Google need to know the Wi-Fi password that I use to, get access? And
what they do is that when you buy a new phone and you log into your accounts, you're automatically connected.
Exactly.
That's the reason why you do it.
Yes.
Your account is already used to authenticate.
Yes.
So that they.
And having said what you just said, Alex brought up a really good reason. It's for backup, right? Backup so it can restore. But the restore has to then require user input. That's the point we're trying to make.
You are providing a username and password at the time of the restore. Like when you're setting up a new phone.
Right, but the content is not secured with that. So if you look at the actual content at rest, the data that's being stored is not encrypted with that password. That's only an artificial protection. It's actually not encrypted. And I'm sure Google will take care of this. This is not, I'm just trying to basically say we're seeing a lot of instances of this. The private key and the public key are being backed up. It's sort of like, why is this, why is it necessary for the server to be knowledgeable about both sides of the equation? And so this kind of makes the server also vulnerable, because it's not necessary, as you said. Exactly, the purpose is to allow the user for continuity. If the user doesn't have the data and doesn't know the password, then they're out of luck, but that allows for a tighter level of security. That's really the reason. By the way, having a password doesn't mean that it's not encryptable. It just makes it a little bit more difficult. And the split key situation that we were talking about, use strong server-side encryption, invisible to the device, split the key material between the device and the server, and the other aspect of it is really using multi-factor authentication, so beyond the password. So how do you identify this user? Stop using password. There are more convenient ways to now identify this user, obviously with OTP, with location verification, with detecting the user's face or voice authentication, and now as we're seeing more and more adoption of fingerprint detection to actually identify the identity of the user that you're trying to ensure their identity. The challenge with some of these multi-factor methods, as bad and as archaic as passwords are, is that they don't always generate the same key. So the beauty of password, as much as we built a company trying to say kill password, is that it always consistently gives you the same key, right? You always type in the same data. Whereas with face, with voice, with fingerprint biometric, you're not guaranteed to get the same data from that user. You're almost guaranteed not to get the same data from that user. So that's why, in terms of the entropy of the key that gets generated, they're very high on the entropy. They're very secure, but they're not the same. The keys are not the same. And so you can verify that this user is who they claim they are, but the information that you retrieved is not the key that you can use to unlock the data. And so that's why the search is still on, and there's a lot of research going on specifically, I found out, at RSA and at other companies similarly, to find out that more convenient, non-password oriented method of creating a high entropy key that can be used to unlock encrypted content. That's really that's a non-result issue. And so, for example, the visual password method, having something that's not typed on the screen. So a lot of people say, well, that's a great method. You just do a visual password. Well, the hackers look at it as a very easy way to hack this, because unlike the keyboard where you can randomize the location of the keys or do a lot of nice things on the keyboard, this one leaves a nice little print where you've actually patterned your device. So just take a picture of the device, look at a different density on the picture, and you can actually see the fingerprint, the location basically that you left on the device in terms of the pattern that you use to lock the device. So there's challenges like that. And so multi-factor mixing that up, having something, being somebody, knowing something, really increases the chance of securing the data and preventing unauthorized access. Obviously, split approach doesn't work everywhere. A lot of times, the biggest challenge is disconnected mode. You know, you want to still access that Google Drive or Dropbox, even though you're in transit or at BARC or on an airplane. And sometimes the split key approach is tough to implement properly, requires service and service to actually work properly to now manage your information. So you have now a third-party reliance that you didn't have before. So just to access your own information. So there's some challenges with the split approach, even though they are very, very secure. In terms of the how, obviously, as I mentioned, either through multi-factor verification or local PIN password, encrypted local data with cryptography, AES, or similar ciphers, and also encrypt the data at rest, in other words, where it's stored, encrypt the data in transmission when you're sending it to somewhere, and encrypt the data at its final destination. But most importantly, do not use the same cipher at rest that you use for transmission that you use for storage. So a lot of pitfalls that we've seen is once one part of the system gets compromised, the secret, shared secret is identified for the information, for what you use to store the information at rest. The programmer was using the same one for transmission and the same one at this destination. So you can actually go all the way to the destination with the same shared secret, as much as this sounds intuitive. That's not what we're seeing. So there's basically a plethora of methods to combine to ultimately arrive at a great method of protecting and storing sensitive information from a mobile perspective. Either you have local storage with password protection. There's a medium level of convenience. The user still has to enter some password. Very easy to implement. It is independent of the hardware OS for the most part. It's very weak. We find that it is very weak in terms of withstanding rooted access, unless you instruct or have the user enter complicated, complex passwords every time they want to unlock the device, and now you have a matter of convenience. Multi-factor increases the level of convenience because now you don't have to enter passwords or remember complex passwords. You can use your face or voice, more natural ways of identifying yourself. What Apple recently introduced, iTouch, and using fingerprint for that method. Increases the level of difficulty a little bit from implementation, makes it a little bit more dependent on the hardware. The ability that that device has to have a front camera, has to have enough of a frame per second capability. All these has to's now start getting introduced into the device. And it increases the level of security as long as you store the information still on the device. With secure elements, you really are increasing the level of security, and you're obviously increasing the level of withholding, being able to withstand rooted access. However, it's a little bit more difficult to implement, and as I said, there's challenges in terms of compatibility across different devices, hardware providers. Ultimately, a secure element, which uses multi-factor, we think has the highest level of security and can really withstand rooted access, has some difficulty in implementation, but ultimately from an end user perspective, it has the same level of convenience. Recommendations in terms of such storage is really start looking more at secure elements, increase the integrity of your data, and really reduce the chance of data tampering is the big deal with secure elements. Avoid NFC for now just because Apple simply decided not to implement it. So if you make your application very much dependent on NFC or use it very specifically, all of a sudden you've made it very specific to pretty much Android at this point in time. Use the split key approach. What does that mean? I get the device, I root it, I have at it, and I can do nothing with it because half the information that is needed to get access to state is living somewhere else with better protection. And also, this type of backup restore using a server helps you with what we just talked about a couple minutes ago, is restoring a disaster recovery type scenario. Just avoid password storage in files because of the variety of methods that are available in terms of compromising and having access to this info, and use the right level of encryption ciphers for transmission and storage of data at rest. Target the latest version of Android. This is kind of like something that's probably not at the discretion of us developers, but ultimately the improvements in 4.3 are phenomenal as it relates to support of secure element, increased security, the key store, and broader third-party app key store support. use multi-factor. We think that that's becoming more and more natural as we see more and more devices start supporting it natively. And the ability to use gestures, the ability to use face, voice, location to determine the identity of the user, and really lowering the reliance on having to enter complex passwords to have access to the data. Make sure that if you're using backup and restore methods, that you read up on whether they are or not storing private key information or full-on unencrypted data for your data access. Some initiatives that I want to take a look at. The SIM Alliance has been a really good one in terms of just overall establishing standards and protocols for the secure element side. FIDO providing a OS-independent multi-factor verification method, and in fact, there's a good level of traction there. Banking, Google, in fact, is one of the board members of FIDO. Cloud Security Alliance, another good one, which is trying to establish methods of highly scalable authentication, heterogeneous cloud providers, so that kind of split key method that we talked about earlier. And obviously OpenID Connect, which is sort of the authentication protocol top of OAuth, based on the OpenID Foundation, and supports Android accounts. There's actually an implementation within Google Code that provides OpenID Connect and is fully supportive of the Android accounts for authentication and storage. Sorry for rushing through this, and wanted to see if you have any questions. We'd be happy to answer that. Go ahead.
So I was wondering if you had a recommendation for a recommended way of sharing secure information between applications without requiring like a network transaction to be able to locally.
Right. The question is ability to share secrets, essentially, sensitive data across applications. And so originally we took the intent approach and basically have the intent. So I'm going to give you an answer which is going to look very complicated. So use a certificate authority, have both applications go to certificate authority and get a certificate. So signed by a CA. Now have application A send its public key to application B over either the binder method or using intent, whatever method you have for sharing. And in that request, the application will say, send me back your public key and encrypt that with the public key I just gave you. So now you have PKI basically going between the two applications. Once that's established, they will cache, store the public keys of each other, and they won't trust requests coming from entities where the key is not signed by the CA other than the keys that they now trusted. So that's established. Now you want to say, I don't want to just use PKI because certificates can be compromised and impersonated, and unfortunately man-in-the-middle attacks are possible. So I want to switch from asymmetric to symmetric and then use that as a mechanism, and I'll explain why we can talk after this. So once you've established public key, you can now send a request saying, use my public key to encrypt a shared secret and send it back to me so I can use that for secure communication. So now the shared secret is created using AES-256 or a nice cipher with great level of cryptography, and encrypted with the public key of app 1 sent back to it. And now the apps start talking to each other using that shared secret. The app that created the shared secret says, I will only honor this shared secret for this many attempts and for this amount of time. So again, after that amount of time, if you go back to PKI to recreate the shared secret. And this asymmetric to symmetric conversion drives hackers nuts. It's very tough to crack, and the beauty of it is in the process you actually use the certificate authority to ensure the identity of the certificate, A, and B, in the creation of the shared secret, you can also use a secure element or a server to actually generate the secret. So there's really well, let's say, established method from that perspective to use PKI and symmetric and mix them up and achieve a high level of encryption. So app A tries to impersonate an app A that was there. Well, it needs to have the shared secret or it needs to have the certificate. You've kind of created a double whammy from that perspective. The other thing that I should tell you is for our secure authentication application, we decided not to use intents. We ended up using binary exclusively. And so The reason is there's just no way for you to get in the middle of that RPC messaging. Whereas in the case of intent, all you have to do is uninstall my app, install a new app, establish the same intent, and you start receiving messages on my application's behalf. And so there's a little bit of a, go ahead, sorry.
But it's gonna still use intents to establish the original binder.
That's correct. That's correct. To establish the original one, yeah.
But once you establish a binder channel, then you no longer really need encryption in terms of the communication, because that's essentially the channel is there.
Absolutely.
Somebody can get in the middle of it.
It's not somebody can get in the middle of it, except for if there's an impersonating app, as you said, who got to establish that channel with you, right? And now, if you send the data in clear text to them, just because they were able to bind to your application successfully, they're stuck instead of getting content in clear text. So you're absolutely
the binding process still requires to authenticate.
Exactly.
Afterwards, you're
I completely agree. So Alex brings a good point, is that once you've established that secure channel, not secure channel, once you've established the bind, now you can start talking clearly. We are paranoid. We're using even basically encrypted content in that secure channel, because we haven't seen what you can do in terms of the rooted device to get in the middle of that RPC message and potentially debug it.
But if you're rooted, then you can also get to the memory of the two processes communicating, where you can get data, in memory essentially.
Correct, but now with the split key or secure element, all you're seeing is information going back and forth, right? So if you're storing information or the key properly, instead of storing it, you're actually not persisting it, you're putting it properly in memory, so it's not easily decodable. So it's very tough to decipher what key is being used. And with this method of constantly changing the key and doing refresh on the key, then you have a stronger chance of protecting the encrypted data. I mean, it's what we're talking about, by the way, is not device specific. The same protocol you can think of a device to server perspective, right? So if you can get in the middle of that tunnel and see the information going back and forth, all you're going to see is garbage. But you're absolutely right. If I can read the memory of this process and decipher where the secure key is being used to generate the key, and do the same on the server, then yes, then you have trouble. But by splitting the generation of the key into secure element for the server, right, then the actual method of generating the key is not visible to anybody.
I was just going to say, like in this case, if you don't care about the key, you just care about the data. The device is rooted, and at some point the data is going to be encrypted and will hit memory. At that point, it's game over. No matter how it was, where it came from.
I agree with you completely. Yeah, for a rooted device, there's so many challenges in terms of cache data or data that's in memory, and now what do you do? However, in order for you to decrypt that data and get to the position of having access to the memory, if you use multi-factor, if you've implemented the proper methods, a hacker with rooted access still has to impersonate the user, still has to generate that key to unlock the data. But yes, in unlocked state, if I steal your device now, if I can root that device without having to reboot it, then yes, there's a high chance of vulnerability, unfortunately, from that perspective. I didn't want to scare anybody, but this is the state we're in, and a lot of great efforts are going on, and as I said, splitting, using secure elements, using multi-factor, avoiding 000 as your password, simple stuff can increase the security of the content. Thank you so much, appreciate it.